OB stars will not live in an OB star surrounding when they are born. Almost all stars of solar mass will be born in an OB association. The OB stars will blow the gas away, and the gravitational binding of the association is lost, and the stars wander out. And when you have people born and they start looking, there isn't any OB star around. But we now know for sure that they were there when the stars were born. And these guys advance OB stars as a possible explanation. And they think it's sort of maybe far out. But we can say that that's not at all far out. That's how it must be. Let's see if I can find the reference to the OB stars. This one's going horizontally here.
Try this one what?
Anyway, these guys have done numerical simulations. However, these numerical simulations require extremely high numerical resolution. 1 million grid points. Okay?
No. Which year was that? 2001?
2002.
Yeah.
Okay?
Like
so maybe we can do better than that, a little bit. And their advanced methods here include cooling and radiation transport and the diffusion approximation. And it turns out that if you take the diffusion time from the center of a disk, the cooling time would be enormous. However, what appears in the models when they make them is convective energy transport. So you really need to get the cooling time by taking the energy content and divide with the surface luminosity. Okay? In which case you get cooling times of the order of hundreds of years only. Okay? So we're in a regime where cooling times and gravitational collapse times are all comparable. And these conditions have been investigated by a number of people in different papers very recently. So this is a topic which is sort of evolving now. I just wanted to see if there are any figures now. Another paper by Boss alone is from also 2002 and explains more about these models of this. Let's see if there are. Yeah, here are some models. So what they're investigating is under what conditions give fragmentation and which don't. And they generally find that fragmentation requires that cooling times are comparable or less than rotation times. Otherwise, we get sort of turbulence, but not really distinct fragments. Okay, another interesting, or these people are actually just commenting on or building on further on work done by Gandhi. He wrote a paper in 2001 where he investigated this analytically. And then we have this paper, which is on Astro PH, Johnson, Young, where they do it numerically and basically confirm what he found before about cooling times and fragmentations. But this is one case where the thing on the right is density, and I think it's a shearing sheet sample. There is also very recently this is papers by in et al. Here. You will find these people who use that most of the time in UCAF.
Oh.
People do SPH. Remind me.
Yeah. What's the name? The guy who does the star formation stuff, and he was in Madrid, of course.
That's the one who was in Madrid.
The name starts with B, I believe. Is that right?
Yeah. Bates.
Bates, yeah, Matthew Bates. Yeah.
Only question. Anyway, these two very high resolution SPH simulations, and they get the same conclusions. But here we learn something more, I believe. Namely that if we have a strong instability, if we set up conditions where there is a strong instability, you get many fragments. That's not surprising, not at all. And now you're again in the position where you would have to say most of these are ejected, and you're left with a few that magically appear in the right positions of Tito's Gordon's law. Doesn't sound very likely to me. So I would come to conclude from looking at these experiments that you need something which becomes marginally unstable. And you get one piece gobbling up most of the mass, and that's it. All it takes to sort of get the Titius body behavior is that one planet gobbles up most of the mass in his regime. One order of two, or approximately two. And then the next guy comes along and gobbles up the rest, and the rest, and the rest. So I think if you look at the papers in the literature that there are papers that work with linear instabilities, they all assume that this is a linear instability which is global and taking place at one time. But that's not necessary. You might as well have scale invariance over time. At first something happens, probably furthest in, but time scales are shortest. And then something happens in the next layer up, and the next layer up. It just has to be scale invariant. It doesn't have to be a global linear instability, which seems a bit far out too.
But it is in some sense global, because the stuff outside knows somehow about the regime of attraction in the inner parts.
Well, yeah, that's debatable. But now over to the other side. I misinterpreted. I sent incorrect information in the email. I'm new at this, so I make mistakes. It isn't 9 orders of magnitude, but there's 11 orders of magnitude, which is lacking in this, what they call the, what's it called now? That's a good paper. Yes, this is the paper that we found from Sten Rasmussen's homepage. And we wrote down star formation, water stacking, the mass barrier. That's where I picked up this quotation. The real problem becomes truly insuperable at meter size. The collision velocity is maximized, and when they're factor 2 apart, they have differential velocities of 3 meters, 30 meters per second, 100 kilometers per hour. We can just imagine from our everyday experience what happens when meter-sized rocks collide at 100 kilometers per hour. They don't stick. Certainly they don't stick. But then these guys in this paper, they develop, I wouldn't call it a theory. And the problem with this entire field is that there haven't been any theories, there haven't been any testable theories. So somebody comes up with an explanation that sort of works in words.
But you said no matter how you bring it together,
the explanation of these people come up with is asphalt. It's tar. They form tar. And then mix the tar with the rocks and they have asphalt. And asphalt is sticky. Okay, so it works. And it's just way out. It's way out. Yeah, it's super good.
But I mean, the temperatures are kind of high, right?
You didn't mention that this is the same way that, I think it's a bit further down here. that this is the same way that tape works. That the stuff that you have on plastic to make it a tape is one of these hydrocarbons that you can carbon.
I think I have a point, because I think the hydrocarbons works for you, but there's something else which is very different.
Okay.
I mean, I just think it helps you.
Yeah.
But you need to know the velocity or anything.
Yeah.
But anything you can think of.
But this is just one of several, not difficulties, but impossibilities in the normal scenario.
I mean, one gets the impression, you know, if you look at the whole thing, it's almost like aake. I mean,
yes,
somewhere there must be a wrong idea, very wrong basic idea in this
from
whole
the
thing.
beginning.
Because now it seems that people are only patching and patching and patching and patching
Yes.
to get the whole thing to work.
Right. And if you look at, I think this is funny. If you look at the about people, I don't know if I can find the formulation, but somewhere it says something like the majority of astronomers believe. Okay, so it's science by democratic vote. And what is said about paradigms? That paradigms are often broken by new people getting into the field. It's perfectly understandable, because people who have been in a field have invested emotions.
Yeah,
They don't want to
change the whole
they don't, yes, they don't want to get rid of their favorite pet theories.
And then to rewrite the code.
Yeah, not to mention that. Right. So this one field I think is very far out. So anybody, is there more evidence for the conventional saga here?
It depends
Something
on.
about the fractionization temperature sequence. But I'm sure that could be
But only,
recycled into the alternative
but only
explanation as well.
you cannot avoid having some kind of grain correlation and transitional formation in some parts of.
No.
I mean, the case for this is extremely strong, I think. Whereas, of course, there's problem with the other
There's no
so we definitely need more than just one theory.
but there's no avoiding forming grains.
No, and you
So
cannot.
grains will be present.
And I mean, the Earth is made out of elements that are hardly present in the universe. So I mean, without grain formation, it would be extremely difficult to form Earth. I think.
The case.
So I think the case for grain correlation and planetesimals is pretty strong in some parts, whereas, as you say, for Jupiter, for example, it's very weak because.
But you need the same explanation. That's.
I don't think necessarily you need the same explanation. You could have a superposition of different mechanisms working.
You wouldn't get a scaling law from a superposition of phenomena.
I don't. Instability. That would be really impressive.
A good place to read is this Boss paper. And what they propose is essentially something we can extend. This is 2/3 the Boss et al. Paper, and 1/3 my extra suggestion. So the new paradigm would be that all planets form by gravity cooling instability. That's the only way you can get a Tizzi's body type of scaling variant formulation. And what Boss et al. Explain is that there is no problem with the gas planets. The only problem is removing the gases from the light gases from the ice planets. And that's a question of removing a small fraction, like 1 out of 12 or 1 out of 15 solar masses in one of the ice planets. And that's why they propose the EUV radiation from nearby host stars. And this is not grasped out of the air, it's grasped out of looking at what's they called, proteins in the Orion Nebula, where we can see this happening. We can see protoplanetary disks evaporating because of the influence of nearby host stars. And that's one of the things that also sets the time scale. But it doesn't take millions of years to make planets. It has to be within a few tens of thousands of years or hundreds of thousands of years.
Well, I would remove it at the inner part of the system before the outer part of the system? I would imagine your O-star would sort of blow it from outside.
Go back to that paper. They say, again this problem apparently. Sorry about that. But they say approximately that sorry about that. I'm waiting for that.